Hello and welcome to my workshop presentation for the paper titled An Interactive Framework for Image Retrieval. This work was done by me, Nikhil Mehta, at an internship at Amazon with Fan Yang, Stephen Rawls, Loris Bazzini, Chengwei Su, and Emre Berg. So, online shopping is a very common medium today. Very frequently people will go to websites like Amazon.com and search for products and buy them and ship them to their house. The common way that online shopping is normally done is customers go to a search engine, they issue search queries to find products that they want, the system returns those products, and then the users look through the products and either buy one of the returned ones or issue a new search query if they don't like any of the products that are seen. But an interesting question is, what if the users like some of the products that they see, but don't like certain aspects about them? For example, let's say they're searching for dresses on a website like Amazon.com, and they see a bunch of dresses that they like, but one of the dresses that they like everything about it except the fact that it has stripes. Or maybe they like another dress, but they want it in sleeveless. These kind of things commonly happen where people like products but just don't like one aspect about it. And it's a very common trouble for many customers because they now have to issue a new query. Well, what can we do to fix this problem? Well, if the user likes a product but not some aspect of it, then they should be able to interact with the system and issue a modification query. The system can then find products that are similar to the user-liked one, but have the modification requested. For example, let's look at the figure on the right. In this case, the user likes a skirt, but it's in orange and the user wants the skirt in black. So the user can select that hey, they like this skirt, and they issue a modification query, which in this case is, I like the skirt, but find it in black. The system should be able to find the similar skirt in black, and thus the user search process is much more seamless. The benefit of this method is that the user now doesn't have to start their search over when they don't like any of the results, and instead they can issue iterative modification queries, and eventually they will be able to find the product they prefer. So they can basically modify the products that they see and search for alternatives that have the modifications they like, which leads to a much better user experience. The formal task definition of this is called multi-modal product image retrieval, and we define this as a task where given a candidate image and a text describing the desired modification, the goal is to find a target image that expresses the modification. In this case, the candidate image was the image on the left, which is an orange skirt that the user preferred. The desired modification query is that the user wants to find that skirt in black, and the target image is the image on the right, which is the candidate image, which is the image that is similar to the candidate image with the desired modification. Prior work works on this problem and tackles it using end-to-end deep learning neural network-based approaches, but these have several drawbacks. Number one, they're challenging to interpret because with neural networks, we can't answer questions easily, like for example, why did the system choose a target image, or what other images were in consideration. Further, it's very difficult to incorporate interactivity, which can be very beneficial because in the case of a mistake, the user can help the system. For example, the user could say, that dress isn't sleeveless, and the system can learn from it even when showing products to other users. Further, users can interact with the system and provide their preferences in an interactive manner, for example saying, I prefer dresses with zippers. The last reason neural networks are difficult is the fact that they don't take advantage of the highly connected structure of this task. In this task, products are often tagged with various attributes and other database measures, which are shared across other products as well, linking these products together. This connectivity would simplify the task of finding a target image given a candidate image with a textual modification, where the task essentially becomes searching for images with a desired modification amongst images with similar attributes. We approach this problem using graph neural networks. We designed this framework through a graph that can be seen on the right. Our graph has product images, attributes for each image, and modification queries offered in text. We connect images with their attributes, and we connect modification queries to candidates they describe the modifications from. The goal is to predict the edge from the candidate from the modification query to the target image. Nodes are initially represented via ResNet or SBERT Roberta depending on their type. The reason we use graph neural networks is because the graph models the connectivity between attributes and images to learn properties and relationships between nodes to solve the task. The task is now extremely simple, where the goal is to find target images that have similar attributes as the candidate but have the desired modification. We can consider an overly simplified example that is shown with the image on the right. Here we see we have a candidate image in a yellow node, which is connected to the attribute pink and summer dress. We are told that we need to find an image that has long sleeves and is more penciled, and is similar to the candidate image. We see that there are 3 potential targets, and we see that potential target 2 is also having the attributes pink and summer dress, and none of the other potential targets have the attributes pink and summer dress, except for potential target 1. However, the reason potential target 2 is the correct solution here is because the caption says that we should find a dress that has long sleeves and is more penciled. And potential target 2 is the only image that is long sleeves, penciled, and matches the attributes of the candidate image. Thus, it is the right solution, and this can be easily found through the graph as shown. We train our model to learn the relationships in the graph so it can solve the more complex versions of this overly simplified problem. And to do this, we train a relational graph neural network with true loss functions for link prediction and compositional image and text loss. To improve this graph neural network and make this problem more interactive, we incorporate several forms of interactivity. In this initial work, we explore 2 forms of common user interactions. The first user interaction is called more metadata. In this case, the user is providing the model with more information about a given product. For example, it could say, "That shirt has long sleeves," or provide any other metadata that the product is not already tagged with. The user interacts by selecting a product and providing the metadata, and technically, to incorporate this into our framework, we connect the product to an attribute with an edge in the graph. The benefits of this interaction is that the model has more information about this image, and this information can propagate through the graph. So the model now has more information about not only this image, but other images and other that have potentially similar attributes. The second form of interaction is called "I like that." In this case, the user interacts and provides the system their preferences. The way the interaction is done is that after seeing the model's predictions, the user can signify if they liked any of the returned products. So the user selects the images that they liked and could potentially buy, and then the model can learn from this that the user likes these images together. And so that means that next time when the model predicts one of these images, it's more likely to predict similar images that have the characteristics of these images because the user liked them in the same context. To incorporate user interactions, we simulate them. For the more metadata interaction, we use attributes from our database. And for the "I like that" interaction, we randomly select images that users may have liked and find similar ones using an embedding similarity measure called face. Our system allows us to incorporate interactions seamlessly where no new training should be required. And the way we do this is we first learn the interactions through a small training set where interactions are done, and then in the future at test time, all we have to do is add a new edge in the graph based on the interaction, and the model immediately knows about the relationship that it had learned, and thus no training is needed at test time whatsoever. We evaluate our model on 2 data sets, Fashion 200K and Fashion IQ. Fashion 200K was synthetically constructed, and the key thing there is that the target image has a 1-word difference to the candidate image caption, and Fashion IQ was constructed where actual humans were interacting. We compared it to prior work, and the results show some improvements, particularly in Fashion 200K, where we see large improvements in recall at 1, recall at 10, and recall at 50. For Fashion IQ, we see small improvements on recall at 100 over prior work. When we incorporate interactions, we also see further improvements. For the more metadata interaction, with just 15 attributes tagged per image, we achieve significant performance improvements in both recall at 1, slightly in recall at 10, and also recall at 50. The "I like that" prediction performance improves, and 65.73% of the time, when we predict one of the predicted interaction image, we also predict the others in the same group, showing that we can incorporate this interaction type. In conclusion, in this work, we proposed an approach to tackle the multimodal image retrieval problem. This was a graph-based approach. We then made it more interactive by introducing 2 forms of interactions in which the user can help the system perform better. In future, we want to have more interactions and also have humans actually do them.